I'll be talking about wireless battery management for EVs and why ISO21434 cybersecurity compliance is essential. All right, I think many of you have witnessed the global shift toward EVs, and by 2040, all right, that there are a lot of predictions that 2/3 of the world's passenger vehicles are going to come from EV sales, right? Now, every EV is really powered by battery cells, and they're grouped into a pack, as you can see in the pictures up here. Now, the pack is usually underneath the chassis, so you don't see it when you buy an electric vehicle. But it is really, this battery really needs to be managed, right, constantly throughout the lifetime of the vehicle, right? Because this battery management system has oversight of all of the functions, and it monitors the health and state of the battery, and it ensures the safety of the driver and occupants, right? Now, there is a trend to move from wired battery management to wireless, right? As you can see on the right, taking out the wires, and we're kind of proud to announce that the first production wireless BMS system debuted in 2021 last year. All right, so this is another system block diagram view of the same system here, and it kind of shows that the communication harness is removed. And for those of you who don't know, typically communication harnesses are manually installed. They're prone to breakage, and once they break, it's kind of hard to repair, right? So we're replacing it with a wireless security network, as you can see on the right. And the architecture on the right kind of shows that it is pretty scalable, to different number of battery modules. So it's likely to work for 400 volts, it's likely to work for 800 volts. Okay, going wireless has benefits, right? So one of the benefits is that it really encourages sustainability. So you can see from this inverted matrix here, and this is a diagram that I took from one of my coworkers' article, right, white paper that is published on the Analog website. So Shana Mahoney, our marketing director for wireless BMS, claims that we need to go with a reduce, repair, and recycle strategy. Right. So this strategy is really important because it helps with three things. Right. The first thing is it really helps to reduce costly vehicle recalls. Right. And the second is it helps to streamline repairs. And the third is if you do encourage battery reuse in second life, right, in a different, maybe non-automotive application, right? What happens is that you might be able to reduce as many as 7 tons of carbon emissions, right, per battery pack. So you can imagine that that really stacks up if you want to be environmental friendly. Okay, so I know a lot of you came here for cybersecurity, and many of you might be experts in the crowd. So how many of you know what's the difference between safety and security? Okay, so quite a good number, right? Now, for those of you who don't know, I think one easy example that I'm going to go through here is really, if you just imagine for a second, you have a wireless BMS system, right? You're driving a car. This is the wireless system in your car. It's designed to be RF robust, right? So no problems with breaking down. It's designed to be safe. In each of the two scenarios that I've listed here, right, would you feel safe to be in the car, right? So that's a question for you if you're an occupant. Now, if we live in a perfect world, right, where there is no malicious actor, everything is supposed to operate as it is, safety shouldn't be a problem, right? What is safe before should remain safe after. But the problem is we do live in a world with hackers, right? And people do want to exploit the system for different reasons, mostly for different personal gain, for example. So the trust of BMS safety relevant data is going to be an issue in these scenarios, right? Where the parts are open, unlocked, you can download code, where the network allows different random nodes to join. Now, the number one fear of applying wireless, right, in a mission critical part of the vehicle is that the worry is that it just constitutes another way for hackers to enter the car, to take control, drive the car off-road, damage all the electronics, right? So I think all of you are probably with me now that you need proper cybersecurity systems engineering, right? The car is a really big system. There are many, many subsystems. And you can see that when we go with systems engineering, right, you're just breaking down, decomposing functionality into smaller subsystems. And many times, the vehicle integrator has to choose from different components, different subsystems from different suppliers, right? Maintaining the quality and the seamless cybersecurity, boundary is going to be a challenge. Now, for a new emerging functionality like wireless battery management, right? This is pretty new. There's no textbook to really tell us how to design this, right? And that is a problem. I've had many, many team members, right, design team members who come to me and say, hey, can I just maybe use a part that subscribes to Evita, right? Maybe that's good enough. And the answer that I have for them is that unless you're able to show that it really meets your intended security goals, you run the risk of an ad hoc solution, right? Now, with ISO21434 that just came out, okay, this is the parallel to ISO26262, which is functional safety. It's the first standard that we're seeing in automotive cybersecurity for road vehicles, right? Now, it really promotes the proper cybersecurity systems engineering approach, where you see the V model here. On the left side of the V, we do requirements capture, proper analysis to get the design. And then on the right, we talk about all the security integration and verification and validation at the top. Now, this standard is definitely more than just clauses 9 to 11 as shown, right? There's a whole life cycle perspective of the product development, right? Which kind of goes from, doing the proper steps on threat analysis, creating the cyber culture, trying to establish rigor in design and test, all the way to managing like vulnerabilities, right? So when you design a product, you need to be aware of what's out there, right? There are new attacks that do apply to your products. You need to be able to respond, react to it. The proper incident response is important. Okay, there are 4 CAL levels. Okay, CAL standing for Cybersecurity Assurance Level, right? So this is like akin to ASIL for those of you who know functional safety. For something that's mission critical like battery management, right? You definitely want it to have the highest level, which is CAL4 here. And the reason for that is because CAL here really specifies the rigor, right, of a product that is that addresses all the threats, right? You want the threats to be properly mitigated to an acceptable risk level, right? So it kind of covers threat analysis, the level of system testing, the level of independence from assessment, as well as the test coverage, right, in terms of vulnerability scanning and even levels of penetration fuzz testing. Okay, so this is the ADI's security design methodology, right? It's a little bit muddled up there. But I know this is a busy slide, but just take you through it. I'm sure many companies, follow a similar flow, right? You kind of have to work it out, pertaining to your application. Now, if you don't know where to start, typically we start at assets up here, right? So up here, because sometimes the security goals are always not totally evident, right? Your customers may give you some security goals, but it may not be the entire set that you want to do because you have internal stakeholders as well. So what we do is we identify the assets, which are typically data. It could be code, that's IP. It could be safety of the passengers within the car. And we identify how bad the impact could be, right? What are the damage scenarios? What are the things that you cannot risk? Then we examine the product, the architecture, the use cases that it is intended for, right, to operate in. And we really look at the life cycle, right, pre-life, in-life, post-life, to really understand what are the different use cases that really require protection of the assets that you are interested in, right? And then by looking at the different ways that the assets could be attacked, right, what we call attack path analysis, are in every kind of threat analysis, we deal with 2 things, right? We care about how likely the attack is going to happen and how damaging that attack could be if it were successful. Okay, there's some cases where one is low and one is high, but all of that feeds into a risk analysis, right? How much risk are you willing to take and how much risk you need to lower it by by choosing the appropriate mitigation. And that will give rise to your security requirements right up here, which in turn then satisfies safety goals, right? So it kind of goes full circle in this sense. Okay, I talked about paying attention to use cases. In many cases, your design is going to be just as good as its assumption. So it's really important to get this right. The battery is usually a passive device, right? There's no intelligence. So the intelligence here really comes from the electronics within the wireless BMS. So here we're basically saying that the wireless BMS lifecycle is going to be very similar to the battery lifecycle because it is intended to enable functionality, enable the battery lifecycle. So the question is, okay, what are the security-related activities and needs here, right, in each of these life cycle states? Some could be apparent, and some may not be, right? So I'm going to pick on one of those, like second life transition. So remember I talked about sustainability, the possibility of battery modules that could have a second life application where they don't meet EV standards anymore, right? So in this case, to support second life, it means that you need to have secure transfer of ownership in some sense, right? And by secure transfer, it means maybe I need to get rid of first life credentials, I need to replace the software, but I need to do it in a way such that I remove any liability of first life from the second life owners, right? And I still need to make sure that second life cannot be exploited by an attacker to attack first life, right? And how you do it does matter, right? The choice of the cipher, the choice of the protocol, the choice of enforcement. Is it just a software solution, or is it really hardware enabled, right? So all of it is going to make a difference. And before we start on any threat analysis, we also need to be very clear about where the system boundary ends, right? So for ADI, we're a supplier to an automotive tier 1. So we are usually a peripheral subsystem of some MCU. We're definitely not the MCU itself. So we need to kind of draw the line between what exactly does the subsystem undertake versus the entire battery management system on the vehicle level, right? And you can see that in our case, the boundary that we have is really this dotted line, right? So we're responsible for safe monitoring of cell voltage measurements, temperature, providing diagnostics, and maybe we handle some of the cell balancing. But the MCU, which is the BMS controller itself, is responsible for safety, is responsible for opening the contactors in the case of a unsafe event, right? So you must have a basic architecture in order to do any threat analysis. Otherwise, you'll be kind of floating in uncertainty when you conduct your threat analysis. So by saying that we have a basic architecture, it means that you must have some idea of form, fit, and function, right? What form does it take, right? How is it enclosed? Is it accessible in any way? The fit must work with the car, with the rest of the system. And function, right? What functions does that system undertake, right? So all of these things matter. And this is an example of a threat surface for in life. Like suppose I've deployed the car, it's running on the road. This is the bigger picture view of where it sits in the car. And there are many approaches that you can take to do threat analysis, right? So here I listed Microsoft Stride, which stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Now, this can be replaced by a different threat analysis methodology, right? You could use, CVSS as a scoring mechanism and using CVEs. All of them should get you to the same place, right? So here we identified the area to be secured. Okay, we'll look at the different interfaces because that's really where data flows, right? Control signals and data flow. And then we try to identify what are the things that matter, right? So if we talk about spoofing, is it because we care about a man-in-the-middle attack, right? And if we talk about physical attack, like tampering, is it because we're worried about device security, right? And then what about access to all the interfaces, right? The wired interfaces and maybe wireless interfaces, right? We're worried about eavesdropping. So as we start listing all of these things down, we answer the questions where and how, right? And that helps to build up your attack path analysis, right? So this is an example of a very basic risk analysis. that is compliant to ISO21434. So we kind of leverage some of the tables for risk determination in Appendix H of the standard. And you can see that in ISO21434, you have to rate it according to safety, finance, operation, privacy. Like, is the impact minimal? Is the impact severe? And how likely it is to happen? So in this case, for an attacker to masquerade as a legitimate node, pretending to be what it isn't, then the severity is going to be high if it succeeds. But the feasibility is actually, feasibility could be high if the network does not enforce any membership, right? So we can say it's high. It may be moderate in some categories in terms of impact and negligible in others. But if you go with the rating here, you can see that the score is 5 at the top. Now, we need to then think of mitigations, right? What do we do about that, right? And you have many choices of what to do, and not all mitigations is going to really lower that score. So we have to really think about what level of risk are we really willing to take. In this case, we can't take a lot of risks, so we apply a mitigation that says we need to enforce network membership, choose the right security protocol, handshake, to ensure that there is authentication, right? So in this case, it kind of lowers our score down to 1, and this becomes acceptable in our solution, right? Back to the stakeholders. So what I've shown here is really like a top-down approach, right? So when you flash it all out, when you work it through, the benefit of this is that you will be able to derive mitigations that are impactful. And by impactful, it means that you don't have any extraneous security features, right? You're justifying to your customer that this is exactly what you need, right? You're not paying for more, and you're not getting less. And here, what sets a good security solution apart from others, right, is really proper systems engineering and careful consideration to make security usable, right? You can end up with a product where security is a pain to use, and that defeats the whole purpose of security design in some ways. So here, I've kind of listed and broken this down, right, into some of the categories here because I want to highlight a few things, right? Now, in terms of security features, you can see that in our solution, we focus on device security and network security, right? And we're very careful about the selection of the choice of cryptographic algorithms and protocols. We want to maintain a constant 128-bit security strength across all of these authentication or cryptographic operations. And we're very careful about not making the key management a huge complexity, right? Making it difficult for the customer to use. Now, with this approach, you're really going to be able to have traceable security design goals, and that is then going to feed into proper validation testing, security validation testing. So we're kind of proud to announce that ADI has achieved ISO21434 certification for a wireless BMS system this year. And one benefit for OEMs to incorporate such a CAL4 certified security element out of context is that it saves on time. It saves on time and effort if a system integrator, if an OEM wants to incorporate this, right? So just to put it briefly, if you have a CAL4 subsystem, it's easy for you to incorporate that in your larger security boundary to make your larger system CAL4. But if you start off with a CAL2, you're going to have to do a lot more work to make that CAL4, right? And hopefully this will accelerate some compliance for Regulation 155, as most of you might know, on cybersecurity risk management for OEMs. And finally, this is a slide just for fun. You see the timeline for automotive safety versus security, right? So in the past, before ISO 26262 was published, you have ad hoc safety. Took some time for adoption, and finally, we're starting to see design and safety. So you can have a similar chart for ISO 21434. And there's definitely adoption time for companies to do so. We have shown that it is feasible to achieve ISO 21434 CAL4 certified products. And there is a lot of commitment coming from different semiconductor players for ISO 21434. And we hopefully should see design and security as time goes by. So finally, CAL4 wireless battery management systems is here. And the question is whether you're ready. All right, thank you.